All right, everyone, welcome back. Today we'll do a review of biostatistics and epidemiology, specifically the way they test these on NBME exams. This can be seen on all the different types of steps as well as your shelf exams. So these are some high yield topics. So we'll cover these in depth. And we'll start off here with the practice question. A researcher wishes to conduct a study to determine if exposure to car exhaust is associated with lung cancer. The study will be used for the purpose of testing this hypothesis as the researcher is unable to find prior research on the topic. They determined that the most feasible strategy for this study includes administering a questionnaire that includes demographics, exhaust exposure, and patient health information, including cancer status. The association between car exhaust exposure and lung cancer status will be evaluated using the results of the questionnaire. Which of the following would be the best choice of study design for the investigation this researcher wishes to conduct? A, case series, B, cohort study, C, cross-sectional, D, case control, or E, and randomized controlled trial. I'll pause here briefly. Okay, so the correct answer for this one is a case control, a cross-sectional study, which I highlighted here, the important features. So the key thing in the question that could give you a tip off is one, that it was a questionnaire that's commonly found in cross-sectional studies. And then the way they frame the association between car exhaust exposure and lung cancer status. So you're assessing for risk factors and outcomes at the same time. You're not conducting one following till the other, which the others studies listed here follow that sort of format. So you can tell that this is a cross-sectional study. And so we'll go into each of these in detail now. So cross-sectional studies, like I said, uses survey data oftentimes and it evaluates risk factors and outcomes at a single point in time. So it's also called a snapshot in time. The pros of this study is that it's cost effective, it's cheap, survey administration is cheap. You can generate a hypothesis, which is what this researcher was doing, starting to find an association, and you can also test already established hypotheses as well. The cons are that you can't determine risk. So the only way you can determine risk is if you start at a point in time and follow people throughout time. Risk is directly related to the amount of time, and so you can't, in a snapshot in time study, determine risk. And high yield for these studies is that they are effective for evaluating prevalence, which prevalence is just the total number of people with the disease divided by the total population. So the amount of people with the disease in the total population. And then key things to look out for are questionnaire or survey. If they say that, unless they're trying to trick you, they most often are pointing towards a cross-sectional study. So this is the oddball. This is the only study that does this snapshot in time and does everything at one point. So these should be pretty simple to catch once you know what to look for. Contrast that with cohort studies. So participants are selected based on exposure status. They're always selected on exposure status, and they're followed over time to develop an outcome, and you measure incidence. So smoking, it would be the exposure status, and then the outcome could potentially be lung cancer. So it can quantify risk. That's a pro because you assess them at baseline, you know they didn't have lung cancer, and then you followed them until they developed or didn't develop lung cancer. So that's how you quantify risk. You follow them over time. You can control for confounding variables as well. You can separate, even though there's two groups of people, exposed and unexposed, you can make sure that none of them also drink alcohol or whatever other variables you want to control for. It's also useful for rare exposures. So why is that? Because you're choosing them based on the exposure status. So if you say, I'm choosing smokers and non-smokers, you're picking the people with the exposure. So it's easy to have rare exposures. We'll contrast that with the case control studies in a little bit. The cons is that they're costly and time consuming. It takes a lot of time and effort to follow people over time. So that always costs money. And then it's not good for rare diseases. So let's say it's a disease rarer than lung cancer. Let's say it's a rare genetic disease that develops over time. You could follow them for 20, 30, 40 years, but if only 1 in 10 million people develop the disease, then that's not a really realistic way of evaluating for that. So it's the opposite. It's not good for rare diseases. And then high yield, the confusing thing with these is they can be prospective or retrospective, but you don't need to, that's not the important part. The thing you need to keep in mind is they'll always be separated on exposure status, and contrast that with outcome status in a case control study, which we'll cover next. So case control studies, participants are selected based on outcome status. So with the same example, they'd be selected based on lung cancer status, and then you'd review records to see if they had smoked or if they had not smoked. So it's the exact opposite. It's the same variables, but you're starting with the outcome and following to the exposure. Again, these are cost effective. Anytime you can use a survey or just look back without following in time, it's going to be cheaper. You can also control for confounding, and it's useful for rare diseases. So if you choose the people with a rare genetic disease, a rare disease, it's if you can't follow them over time and hope that they develop that disease, that's just not likely. It would be a 1 in a million chance. But if you find the 10 or 20 people in the world that have that disease and then compare their exposures, that'd be much easier. So it's useful for rare diseases. So it's an easy thing to remember here is case control studies are selected based on the disease. That's why they're also useful for rare diseases. Contrast that with cohort studies, which are useful for rare exposures, and they also select based on exposure status. The cons are you can't determine risk. Again, you're not following them in time, you can't determine risk. And then it's not good for rare exposures because you didn't select based on the exposure. You're going to look back and hope that you find some rare exposure that's not realistic. You'd have to choose those people to be able to find those at any reasonable rate. The high yield thing for this is that it's an exposure odds ratio that's a measure of the association. People get this confused a lot. So what this means is that it's the odds of exposure among disease compared to those who do not have the disease. So it's another term for the same thing, but people say odds ratio, but it's specifically an exposure odds ratio that you're calculating with case control studies. Moving on, we have case series and case reports. So case reports are easy. You just document a single person with the disease and all of their risk factors. And a series would be a handful of patients with a similar case. So these are cost effective, right? They're much faster. You can just evaluate these people in a short period of time and write them up. The cons is there's no group to compare them to. They're just cases. You can't compare. You're not comparing them to a control. So it's just case series, not a case control. And then the high yield is these are often used in infectious diseases and outbreak investigations. So if you have an outbreak of salmonella or something on a cruise ship, you can take all of the people who had that disease and you can compare their exposures, and it's just the cases themselves. There's no controls. And then last here, we have randomized controlled trials. So these are the only interventional of the studies we've talked about so far. The previous were observational. You're looking at information that they're giving you. You're not doing anything. Individuals with disease of interest are randomly allocated to receive an intervention. So you're giving them something, is the difference with the randomized controlled trial. So remember, these are the gold standard of study design. You can directly quantify risk, and you can pretty much eliminate confounding if you do these correctly. You randomize them, so participant A can be randomized to group 1 or 2, B 1 or 2, so on and so forth. So when you do that, the chances of people having confounders like gender or age, they all get randomized to the groups. So you are immediately controlling for those confounding because you're randomizing. The cons are these are the most expensive types of studies, and they can often have ethical issues. For example, if one treatment is found to be harmful or not as effective in a research study, you can have the study shut down if the results are so significant that they've found earlier in the study. So there can also be ethical issues here. And keep in mind what blinding means. So single blind means that the participant in the study does not know which group they're being allocated to. That's important because if they did know, then if they weren't in the treatment group, they could potentially leave the study. If they were in the treatment group, they could potentially give themselves other treatments to influence their results. Double-blinded is where the participant and the researcher don't know. That way the researcher can't impose their own bias on the study. And then triple-blinded, which is oftentimes not feasible, so double-blinded is the gold standard. Triple-blinded is where the investigator that's analyzing the data also doesn't know the treatment group. But that's not feasible because oftentimes you need the person analyzing the groups to know who is in which group. So those are the basics of study design. So we'll talk now about a common topic that comes up with randomized controlled trials these days, and that's intent to treat versus per protocol analysis. So these are both ways in randomized controlled trials that you're evaluating participants and you're comparing the groups, so the treatment group and the control group. With intent to treat, it's exactly like it sounds. So in the group that participants were randomized, either group 1 or group 2, even if they leave their group, they're analyzed like they're still in that group. Contrast that with per protocol. So this only allows people who adhered directly to the protocol to be analyzed. So we'll talk about an example here on the next slide, but let's just finish the pros and cons. So intent to treat, if you think about it, this is a more realistic real life world strategy versus per protocol is the study that works better in a vacuum. So the pros of intent to treat is it preserves sample size and preserves randomization, but it can't underestimate the effect. Versus per protocol can overestimate the effect because it's choosing a study that would be in optimal, perfect conditions, which oftentimes isn't right in the real world. So it may overestimate the effect. You also may have selection bias in per protocol studies, and you may reduce the sample size because you're only allowing those who adhered to the study to be analyzed. So let's think about these pros and cons, and we'll do an example here on this slide. So we have the treatment group here, and we have the control group. And we're going to use this one individual. Let's say there's 5 individuals in both groups. Obviously, the sample size would be too small, but just for the sake of example. Let's say this person in the treatment group has a really adverse effect and decides to leave the study. So they are removed from the study. So if you picture this person being gone, we now have 4 in the treatment group and 5 in the control group. In an intent to treat analysis, you treat this group like this person didn't leave and you still use the data as planned. In a per protocol analysis, this person, once they leave, you remove them from the study and you don't factor in their information. So at the end of the study in a per protocol, you may say, oh, wow, this treatment group had really great outcomes, but you are completely excluding this person who may have left the study because of an adverse effect. So that's not realistic in real life because people will leave the study or people will stop treatment if they're having adverse effects. So that's why this is useful in a vacuum where if people don't leave, but in real life, people may leave the study, they may have adverse effects and things like that. So intent to treat would keep this person in the group, preserving the group that they were randomized to. Again, if this person leaves, they're removing their randomization. They were initially randomized to this treatment group and they're leaving that group. That in a per protocol study, that's completely violating randomization versus in an intent to treat, you say, hey, we're keeping you in this group and you can leave the study, but we're still going to analyze your data as if you're in this group. And so that's the difference between intent to treat and per protocol. Intent to treat is a real life, realistic way of evaluating for how studies or how real life is, medication being given to patients in the real world. A per protocol study is in perfect conditions and can test how optimally your drug can work if there are no other variables such as side effects or adverse effects, things like that. So think about that, and then you don't have to memorize the pros and cons. You can just keep those in mind. So we'll move on now to measures of association. So here are some common measures of association that are used. We have risk ratio, odds ratio, and then the hazard ratio. So risk ratio are used in cohort and randomized controlled trials. So again, these are studies that can quantify risk because you're following them over time. You always need time to evaluate risk. So you basically compare who developed an outcome in those who were exposed, and then you divide that by those who were unexposed. So it's a ratio. And then the formula here is A over A plus B divided by C over C plus D. So you're comparing risk in exposed and you divide that by risk and unexposed, and it's a ratio between the two. Odds ratio is similar in that it's a ratio, but instead of the risk, you're comparing the odds of an event. And so these are used in case control studies. Remember, case control studies are not following patients over time, so you can't quantify risk. So what you do instead is you compare the odds of those in one group compared to the odds of those in another. So you divide A divided by C divided by B divided by D, which the common formula you end up with is A times D over B times C. We'll get to how to work the formula out shortly. And then hazard ratio is similar to risk ratio. It's a ratio of an outcome compared to those exposed versus those not exposed, but it is over a period of time. So risk ratio, you need time to evaluate risk, but hazard ratio can directly allow for person time. So if someone discontinued from a study halfway through the study, you would be hard to calculate their risk, but with a hazard ratio, you could use the time that they were in the study and to compare the hazards that they experienced within that period of time compared to those who didn't. And so these are used in survival analysis. Survival analysis is basically saying how many people are alive at varying points in the study. It doesn't have a single endpoint. The whole study is an endpoint. So there's 1 year, 5 years, 10 years, and that sort of thing. So it's very, very similar to risk ratio, but it's used in survival analysis. Let's briefly touch on statistical tests now. So the easiest way to think of statistical tests is think about what kind of variable are the independent and dependent variables. Are they categorical? Are they continuous? And you can easily figure out the test from that point. So for a t-test, the independent variable is categorical and it has to be two groups usually. So let's say, for example, comparing males and females. The dependent variable has to be continuous. So let's say comparing mortality rates between these two age groups. That would be a t-test. Contrast that with analysis of variance, or ANOVA, which is almost exactly the same. The difference is that there's 3 or more categories. So instead of male or female, you could use male, female, non-binary, and you compare the dependent variable, which could be the same thing, mortality rates. Versus chi-squared, which is the independent variable is categorical, 2 categories usually, and the dependent is also categorical, such as tall or short. So the difference here is both variables are categorical. Linear regression, the independent variable can be either categorical or continuous, but the dependent variable has to be continuous. So you're basically plotting between the independent variable, whether that's categorical or continuous, you're plotting on a line, you're comparing those variables' dependent outcomes on a continuous scale. And linear is different than logistic regression because logistic can also have the same independent variable. It can be categorical or continuous, so that's not a differentiating factor. But the dependent variable is categorical, so it's 2 groups. So you're plotting, again, just like regression, you're plotting on a line, but instead with logistic regression, instead of plotting on a continuous line, you're plotting one group compared to another. So that's how linear and logistic regression are comparable. Logistic regression doesn't come up often, but the way it would come up if it does is that there's 2 categories as the outcome. Keep that in mind. So you can always tell these apart just based on the independent variable and the dependent variable oftentimes, and then usually just based on what the study is trying to find, you can differentiate these 2. Let's talk about confidence intervals. So confidence intervals are a range of the values that are likely to contain a true sample measurement. And so you'll see 95% or 99.7% as common values here. And so keep in mind that you're always trying to compare against a null value. So if the study is trying to measure a difference, so the difference between the mortality rates, drug A versus drug B, the null value is 0. X minus Y equaling 0 would be the null. Versus if the measure is a ratio, so if you're comparing the ratio of mortality between group A to group B, you're dividing A divided by B, and 1 would be the null value. So keep that the null value can be different depending on what the study is in mind. And so how do you find statistical significance? So it's significant when 2 confidence intervals don't overlap. So you have one interval here and one interval here. And if there's no crossing of their bars, you know that that's significant. Or when a single confidence interval doesn't include the null. So if you have a confidence interval here, and then you have 0, and it doesn't include 0, you know it doesn't include the null. But if there's a ratio, such as a risk ratio, you have to look for 1. So that's why it's important to keep the 0 and 1 in mind. It's the null value that you're looking for. And then not significant is when the 2 confidence intervals overlap or when a single confidence interval includes the null value. And so where people get tripped up oftentimes is interpretation. So there's many ways to interpret confidence intervals, but all of these are valid options. So the most common one is this first one. We are 95% confident that the true population mean lies within this interval. That's what a confidence interval is trying to tell you. That how confident are you that the mean that you're testing for is truly within this range? You're 95% confident. You could also say if the study were repeated 100 times, you'd expect 95 times the true population mean to lie within this interval. So it's much of the same thing. It's all related to 95%. Or on the contrary, you're saying that only a 5% chance that the same or a more significant value is obtained due to random chance. And so this option 3 is directly talking about p-values, which we'll talk about here in a second. Keep in mind, easy things to keep in mind for confidence intervals is this is the mean here is mu, and then this is standard deviation. So one standard deviation away from the mean is a 68% confidence interval. 2 standard deviations is a 95% confidence interval, and 3 standard deviations is a 99.7 confidence interval. So if they say, what's the 95% confidence interval for this, and they give you the mean and standard deviation, you can usually just calculate. You can move the standard deviation. So if the mean here was 100 and the standard deviation was 5, then you know that 95 and 105 are here, and you know that 90 and 110 are here. And you can just basically create the interval just based off of the mean and standard deviation. They often give it to you like that. And so let's talk about p-value now. So p-values are the probability that a value obtained in a sample will be observed if the null hypothesis is true. And that sounds confusing, but it directly corresponds with the confidence interval. That's the easy way to remember this. So it's set at an alpha level of 0.05, which what does that mean? It basically means a 5% chance of falsely rejecting the null hypothesis, of basically a false positive, of falsely concluding that there was a significant finding when there wasn't. It's the exact inverse of a confidence interval. So this is also corresponds to a 95% chance of correctly rejecting the null hypothesis. So see how a 95% confidence interval directly corresponds to a p-value of 0.05. And so that way you say if a p-value is less than 0.05, meaning we say that there's less than 5% chance that this is due to random chance, then we call that statistical significance. So a 95% confidence interval and a p-value of 0.05 or 5%, they're directly corresponding to each other. And you can use the same thing, the 99% confidence interval, it would be a 0.01 p-value or a 1% value of alpha. So p-values and confidence intervals directly correspond. And so the interpretation would be the same. So if the p-value is less than 0.05, you say that the finding X is statistically significant. Okay, so let's touch on 2x2 tables now, and we'll talk about a lot of the measures of associations we talked about previously. So here are 2 styles of 2x2 tables you'll see all the time, and you can just briefly draw these and figure these out easily on exams. So this first one here, you have in the left side, you have exposed and unexposed, and then you have diseased and no diseased here. And then here's the other version here is the test. So if you're trying to evaluate a test for sensitivity and specificity, you have the test positive and the test negative on the left. And on the top, you have the true, which is the gold standard on the top, and the gold standard negative. So gold standard confirms to have the disease and confirms to not have the disease. So these are the 2 styles of 2x2 tables. And then you calculate A, B, C, D, and you add it going this way, you add it going this way, you add it going down, and then this is the total here in the bottom right. So let's use these into some examples. So we talked about risk ratio. So risk ratio, here's the formula. It's easy to remember, but the important part is to figure out why this formula is true. So this is the row you're using A over A plus B. So you're saying who has the disease compared to who doesn't have the disease amongst a total group of exposed. And you're dividing that, comparing that to the unexposed. So you're saying who is developing the disease among the exposure divided by who is developing the disease without the exposure. And so that's a risk ratio. You're comparing the risk of disease to those from those exposed to those unexposed. And so that's an easy formula. You basically do A over A plus B and you divide it over C plus D. And then there's odds ratio, which is basically saying what are the likelihood of developing the disease. But since you can't calculate risk, you say among those with the disease, how many people were exposed, and you divide that by how many were not exposed. Then you divide that number by with those who don't have the disease, who was exposed and who was not exposed. And so if you divide those out, if you do your basic math here, you find that A times D divided by B times C, this is the same formula. So oftentimes what people do is cross multiply. You can calculate an odds ratio by saying A times D and divided by B times C. So that's the easy way to figure out the odds ratio formula. But if you break it down, you can understand why those formulas exist if you ever get confused about the formula. So now we have the way to calculate sensitivity, specificity, and positive predictive value and negative predictive value. So now we have the test on the left, either positive or negative, and then the true gold standard on the right, on the top, which is positive or negative here. So sensitivity is highlighted in red here. So what you're saying is, among those with the true positive test, so gold standard positive, how many of them tested positive compared to those who tested negative? That's what sensitivity is testing for. Specificity is the exact opposite. You're saying, among those who truly do not have the disease, this should be a D here. This should be a D divided by B plus D. Among those without the disease, how many of them tested negative versus testing positive? So what you're trying to find, a perfect test here for sensitivity, this A would be 100 and this would be 0. A perfectly specific test would have a D value of 100 and a B value of 0. So this B value is the same thing as a false positive, and this C value is the same thing here as a false negative. So the A and the D are the good. You want these to increase in the setting of sensitivity and specificity. So this should be D over B plus D. And then positive predictive value and negative predictive value is the exact opposite going across here. So you're comparing, this is a measure of the test itself, and it's also a measure of the prevalence in the community. So A over A plus B, so you're saying, among those who test positive, how many of them truly have the disease and how many of them truly do not have the disease? And so this directly varies with how many people in the population truly have this disease. Contrast that with sensitivity and specificity, which are truly just evaluating how the test is, because you're comparing a single group of those confirmed to be positive. And the negative predictive value is pretty simple. It's the same thing over here. So again, this should be D over C plus D here. So you're comparing, you want the test to be negative if it's a negative predictive value, and then same is true for positive predictive value. So don't mind the formulas here at the bottom, just use the box here at the top. And so final points here for sensitivity and specificity. Sensitivity, the mnemonic is snout. So highly sensitive tests are effective for ruling out disease. And why is that the case? Because if we go back here, if a test, if this is sensitivity and a test has 100 here and 0 here, that means if that sensitive test is positive, that means you essentially have no one in that test who tested negative. And so you've essentially ruled out that disease, and vice versa for specificity. So highly specific tests are effective for ruling in a disease. So you use the same thing, the same idea there in the formula. So oftentimes in studies, they use a sensitive test first as a screening measure. Keep that in mind, that's high yield. And then use a specific test afterwards to confirm or rule in the disease. For example, hepatitis C, you can use the rapid test to test for and confirm and rule out those without the disease. Then if anybody tests positive, you would want to confirm. You've ruled out people without the disease, but you want to confirm now that they have the disease with the highly specific tests. And so you would use an RNA test at that point, for example. And keep in mind, positive predictive value varies directly with prevalence. So as prevalence increases, positive predictive value increases. And then the negative predictive value, as prevalence increases, as more people have the disease, less people will test negative, and so the negative predictive value varies inversely. So we'll cover some plots and graphs here now. The scatter plot here, so this is used to establish correlation. It's used in ecologic studies. So ecologic studies we haven't talked about, but ecologic studies are using populations or groups as the measure instead of individuals. So it would be if someone was comparing the GDP between country X to country B, that would be an ecologic study. So keep in mind, this uses a correlation coefficient. It ranges from -1 to +1. -1 is a perfect inverse relationship. So that would be if the line was directly pointing down this way. And a +1 would be a perfect direct relationship if the line was pointing straight up from 0 here. So this is closer to 1 than it is to -1. And if it's greater than 0.5 or less than -5, it's a strong relationship. So there's a correlation. So I'd say this is strong. It's probably greater than 0.5, but it's not quite 1. And then if you square that correlation coefficient, so if you square 0.5, you would get the coefficient of determination. So how much of this variability in variable y is determined by variable x? That's what r squared means. Then we have funnel plots. So this is a good way to measure for publication bias. So they plot each of these points here is the result from a study. So you can think of each of these dots as a separate study. And so if the results are asymmetric in the funnel, you know that there's asymmetric, which indicates bias usually. And so this often happens when publication bias is where basically only studies with a significant effect are found, and there aren't any in this group here. You would say that people are only publishing the studies with significant findings, as opposed to there should be at least a few studies here, even if there are more here. And so the more asymmetric it is, the more you could potentially have publication bias introduced. Then you have forest plots, which are used in meta-analyses. So 1 here is the null value, but again, keep in mind that that's for a ratio. If it was a difference, 0 would be the null value. And so this study here overlaps the null, so you know that this wasn't necessarily significant. And then this diamond here is basically the summary measure. So you combine all the studies and you see their effect. So this is basically combining the effect of all of these studies into a meta-analysis. And so you can tell that 2.2, the odds ratio is greater than 1, which is the null, and the confidence interval 1.9 to 2.4 does not include 1. So you know this is a statistically significant finding here in this meta-analysis. So it's using the same thing as before, confidence intervals and p-values, but it's combining the efforts of multiple studies to increase the power. And so then we have box plots. So the box here, and then you have the stem, and then the max, and then the min. You have the first quartile, the median here, which is the second quartile, the third quartile, and then the fourth quartile here. The interquartile range is the third quartile minus the first quartile. And so this is useful for continuous data, and you can easily see outliers. So this should say outlier here. So if there was any points way off of here, you would know that that's an outlier, or if there were some below the minimum, you know that's an outlier, and you can oftentimes adjust for those outliers and see them really easy visually. Then we have histograms. So we have a variable, a continuous variable going on the right, and then we have frequency going up here. So this can be confusing. So because it's not two different variables, it's one variable and then frequency. So for example, between 60 and 65, there's 3. Count up, there's 1, there's 2, there's 3. So you can also count the total number of individual cherry trees in this example. So it'd be 3 plus 3 plus 8 plus 10 plus 5 plus 2. So you can count up the total number just by looking at a histogram, which is different than other studies, other graphs. You can't necessarily count up the total number of participants in a study. So last year, we'll talk about different kinds of bias, different categories, and some quick examples. So sampling bias is essentially saying the study sample is non-randomly selected from the target population. For example, from a population of smokers, individuals are selected via a phone call to participate in the study. So the problem with this is that only those who have a phone, who can communicate clearly, and those healthy enough to participate are included. So you're unintentionally excluding people from the study. It's not a perfect example, but you can see how just using a sample method that doesn't get a random sample of the population can potentially bias your results. So it's easy to remember sampling bias because you know that the idea is that you're sampling incorrectly. If I go and assess a questionnaire at those at a college, but I don't give it elsewhere, I'm sampling from college students. That's not going to be representative of everybody. So that's what sampling bias is. Then we have non-response bias, which is exactly how it sounds. Individuals do not respond during the course of the study. So this is a common problem in retrospective and cross-sectional studies when you're basically assessing people with the questionnaire a lot of times. And so, for example, those affected by a mass weather condition are emailed a survey to evaluate for comorbidities. The problem is those with significant psychiatric conditions or lost economic resources may be unable to respond. And so you've basically selected by if you don't evaluate those people who don't respond, those people may be inherently different than those you included in the study. So all of these biases come down to in information that there's an issue with those who don't respond or with those who aren't included that are different from those that are in your study. Attrition bias here. So this is also known as loss to follow-up bias. So this is essentially the same thing as non-response bias, but how it works in a prospective study. So those are included in a study, but then they eventually leave the study. So for example, those exposed to potential toxic herbicides are followed to the development of cancer. So the problem is those who die or become very, very ill will be lost to follow-up. And then those in the study now are only those who are healthy. And so you falsely conclude a weaker association than that truly exists because you lost people from your original study. And then Bergson's bias here. So individuals are included in a sample from a hospital population, and they're generally more ill than those that are than healthy individuals. So it's also known as admission rate bias. So this is pretty easy to think about because those in a hospital are generally more sick than those not in hospitals. So for example, if you screen newly admitted patients with an EKG to study underlying heart rhythms, and you say there's a significant benefit, the problem is that if you try and apply those results to a general population of people, that won't work because hospital patients are generally less healthy. So an EKG into the hospital may be helpful, but screening people at home with an EKG may not be worthwhile because they may be healthier than those in a hospital. So Bergson's bias, think of hospitals. Then we have recall bias. So those with awareness of a condition may increase their ability to recall specific risk factors. So think about retrospective studies, specifically case control studies. So a classic example, mothers given birth to infants with neural tube defects compared to those without neural tube defects are given surveys about food exposures. So the problem is mothers of those with neural tube defects in this example may remember a lot more about food exposures than those who do not have neural tube defects. Observer bias. So this is the researcher, the observer themselves misclassifies data due to different interpretations or their own beliefs. So a researcher interviewing patients in an RCT with a subjectively reported pain scale. So let's say this study, they weren't blinded and the researcher is aware of their treatment group. The researcher could unintentionally or intentionally encourage the participant to change their pain scores. So that's observer bias. The observer themselves is influencing the data that's being classified, whether by changing their responses or changing it themselves. That's what observer bias is. That's pretty easy. So the observer, the researcher, is the one introducing the bias. And then last here, we have surveillance bias. So the risk factor itself increases monitoring in the exposure group. So example, smokers are supposed to be annually screened for lung cancer with low-dose chest CT. The problem is that the incidental finding of lung nodules can be more common in those screened for lung cancer than those not being screened. So because a group was undergoing surveillance, they're more likely to have discovered an outcome than those not being screened in the first place. So that's what surveillance bias is. When the fact that you're surveilling people increases the likelihood that you'll find something compared to those not being surveilled. So that concludes everything I have for this video. We didn't go through too many practice problems, but I went through a rapid review. If you go back to the internal medicine shelf review video, I did a rapid review with many of these topics being covered, but I wanted to cover the concepts particularly in detail. So there may be a part 2 of this to follow if this was helpful, so we can cover more topics like this in the future. So don't forget to like and subscribe if you found this helpful, and comment below if you have any other suggestions or any other video ideas.